We're going to talk about balancing redox equations in acid solutions. This goes along with the worksheet called Balancing Redox Reactions. It has 4 problems on it. We're doing a different problem. Here's the method to balance oxidation-reduction equations in an acid solution environment. It's very useful for balancing reactions between ions when you have hydrogen ions present. This is an old way of remembering oxidation-reduction reactions. Oil rig. Oxidation is loss, reduction is gain. In oxidation-reduction reactions, one species loses electrons and another chemical gains electrons. In acid solutions, many oxidation-reduction reactions will take place, because if these reactions require hydrogen ions, the hydrogen ions are present from the acid. And if they need oxygen atoms, you have those in the water molecules. For example, and this is the example we will work, the oxalate ion will react with chromate ions in acid solution. The unbalanced or skeleton reaction is this, and we're showing the net ionic equation so that you don't have to fool with the spectator ions like potassium and chloride. Oxalate ions react with hydrogen ions and chromate ions to form chromium 3+ ions, water, and carbon dioxide gas. You may already know that the oxalate ion is really just 2 carbon dioxide molecules stuck together with a couple of extra electrons. The first step, almost the 0th step, is to assign oxidation numbers so we know what's being oxidized and reduced. So we'll do that now. Since oxide here is -2, we have -8 total, of which 2 negatives are left over. So we have to balance off of 6 negative charges, and we have 2 carbons to do it. So each one of these oxalate carbons must have a formal charge or oxidation number of +3. On the other side, the carbon dioxide carbon, and we all know, is +4. Therefore, a change from +3 to +4 must involve a loss of electrons. This is the oxidation. Using the same equation, looking at the chromium, since the oxide is -2 and 2 of them are left over, each chromium must have a +6 oxidation number. On the right side, though, we can see immediately that the chromium ion is a +3. The change from +6 to +3 involves a gain of electrons. This is a reduction. Our next step, or part of this step, is to split the reaction into half reactions, the oxidation and the reduction. The oxidation of the oxalate, it breaks up into carbon dioxide, but we have a charge of -2 over here, so electrons must be lost, and we can see there are 2 that need to be lost. This is the oxidation half reaction. Continuing, reduction is of the chromate ion. It breaks up into the chromium 3+ and water. To do so, though, to make water, you have to react hydrogen ions with these oxides here in the chromate. And we need to balance that half reaction with 8 hydrogen ions for the 4 oxides, making 4 waters. But electrons must be gained, 3 of them. So we have a -3 here and a +8. That makes +5. And then we're going to subtract 2. So that's +3, and now we have +3 over here. So our charges are now balanced. This is the reduction half reaction. Step 5, we've already done the other intermediate steps. We're going to make the electrons that are lost equal to the number of electrons gained. So here are 2 half reactions. You see we're giving away 2 electrons. we're taking in 3 electrons. That's an unbalanced situation. The lowest common multiple of 2 and 3, of course, is 6. So we must give and take a total of 6 electrons. That means we have to multiply the oxidation half reaction by 3 to get 6 electrons coming off, and the reduction half reaction by 2 to get 6 electrons being taken in. Step 6 is to add the half reactions and clean up. As you can see, here are our 2 half reactions properly balanced for charge. The 6 electrons given, 6 electrons taken. Now they are not in the picture anymore because that happens in a sense behind the scenes. So we're going to knock them out, and then we are going to add the 2 half reactions together to get 3 moles of oxalate reacting with 16 moles of hydrogen ions and 2 moles of chromate to form 6 moles of carbon dioxide gas, 2 moles of chromium 3+, and 8 moles of water. Note, when we do these reactions, we have to have plenty of acid available because a lot of these reactions require huge amounts of acid or else they won't work correctly. Step 8 is to check the atom and charge balance, something we always do when we balance equations. We have 6 carbons on the left, we have 6 on the right. We have 20 oxygens between the 2 species on the left, and we have 20 oxygens between the carbon dioxide and oxygen of water on the right. We have 16 hydrogens on the left and the right, and we have 2 chromiums on the left and on the right. We are now working with a completely balanced chemical equation, a net ionic equation, for the reaction of oxalate and chromate in an acid medium. We use this method to balance equations, redox equations. It's time consuming, but if you try to do something like this by inspection, you'll probably grow very, very old before you can get many of them done.